Hello my dear students, this is Roshni from LearnoHub, the free learning platform, www.learnohub.com. So today I am here with the fourth video and the last video of the video series on electricity class 10 science, and in today's video I am going to talk about Joule's law of heating or heating effects of current and electric power. Besides, I am also going to solve a lot of numericals based on these concepts. So quite important one, and numericals are anyways very important in physics. So let's watch this entire video and let's learn together. So are we all ready? Let's get started. We will now talk about heating effects of current. So what actually we are going to study in this topic is that whenever electric current flows through a circuit, there is some amount of dissipation of heat which takes place. So now we will see that how is that heat utilized in different kinds of electrical appliances. So what do we mean by heating effect of current? It means dissipation of source energy in the form of heat in an electric circuit. As I mentioned before, in any electric circuit, there is a source of energy. For example, when I talk of this electric circuit which you see here, you have this battery. So this battery acts as the source of the potential difference, right? It provides the potential difference. And because of this potential difference, there is an electric current which flows in this circuit. Now the amount of energy which comes from this source, some portion of this source energy is dissipated in the form of heat. So this is known as heating effect of current. So now we will see how is this dissipated heat utilized in many different ways. So let us consider this circuit, and let us suppose that current I flows through this circuit. When this key is closed, some amount of current I flows through this circuit. So current flows through this resistance R, right? So let us say work done in moving a charge Q through a potential difference V. Let us suppose the potential difference provided by this source is V. That is the potential difference between these 2 points. That means right now we are concentrating across this resistor. We say that amount of current through this resistor is I and the potential difference across this resistor is V. So what is the work done in moving a charge Q through this potential difference V? What would be the work done in moving a charge Q through a potential difference V? What will be the work done? That will be equal to Q into V. That is charge into potential difference. So what is the power input to the circuit? How much power is provided to the circuit? Power is always equal to work done per unit time, right? So work done is Q into V divided by time. Now charge per unit time is current. So this is equal to VI. So therefore we can say that this is the power, this much is the power supplied to the circuit. So how much is the energy supplied to the circuit? The energy supplied to the circuit will be equal to power into time, because power is nothing but energy per unit time. So this will be equal to VI into T. So this much is the total amount of energy that is supplied to the circuit. So we can say this is the total source energy. Now this energy is dissipated as heat across this resistance R. So how much is the heat dissipated? Heat dissipated H is equal to VIT. Now from Ohm's law we know that V is equal to IR. So we can put V is equal to IR. So we get H is equal to I square RT. This is known as Joule's law of heating. This is called Joule's law of heating. So according to Joule's law of heating, if you have a circuit where there is a source which provides some amount of source energy because of which a current I flows through the circuit, then the heat that is dissipated across the resistor is given by I square RT, where R is the value of that resistance and I is the current flowing through the circuit, right? So this heat is useful for many different applications. We will look at some of those applications in the next few slides. So from Joule's law of heating, what did we conclude? We conclude that the heat produced in a resistor is directly proportional to the square of the current, because H is equal to I square RT. So it is directly proportional to square of current. It is proportional to the value of resistance for a given current. It is directly proportional to the time for which the current flows through the resistor. So this also tells us that if current keeps on flowing through a circuit, the resistor gets heated up gradually, right? Because some amount of heat is getting produced across the resistor. So the resistor will get heated up in due course of time. Let us now look at some of the applications of heating effects of current. That means the heat which is dissipated when electric current flows through a circuit, we will see how does that heat get utilized for some important applications. Examples of such things would be electric heater, electric kettle, electric iron, electric bulb. All these things make use of heating effects of current. So let us look at this electric bulb. If you observe an electric bulb closely, you would see that there is a filament inside the bulb, and that filament retains most of the heat that is generated during the flow of electric current through the circuit. So whatever heat is generated across the resistor, that is stored by this filament, and this filament is made up of tungsten. Now why is it made up of tungsten? Because tungsten has very high melting point, so that even though it accumulates so much of heat in itself, it does not melt. So what happens? The filament becomes hot, and when it becomes hot enough, it starts emitting light. So in a bulb, you have a filament made of tungsten. So this filament retains most of the heat generated, and when it becomes sufficiently hot, it emits light. So now what we do, this tungsten, this filament is thermally isolated so that so much of heat doesn't damage the other parts of the bulb. Most of the power consumed by the filament is given as heat, and a very small portion of it is given as light. So most portion is given as heat and some is given as light. Right, so in this way we see that in bulb, electrical energy also gets converted into heat energy and light energy. Let us look at another important application, that is electric fuse. You would have seen that there is something called fuse at your home. What is the purpose of the fuse? It prevents excessive flow of current through the circuit. As I mentioned, sometimes excessive flow of current can damage the different components present in the circuit. So in order to prevent that, fuse is used. So fuse is connected in series with a device, and so because the amount of current which flows through, if you connect two things in series, same amount of current will flow through each of them. So let us suppose if some excessive amount of current I is about to flow through the device, the same current will have to pass through the fuse first. Now what does a fuse do? Fuse is nothing but it consists of a wire which is made up of some metal of specific melting point. For example, this kind of fuses are the ones which you generally see at your homes. So if you see, it consists of a wire, this wire. So this wire is made up of a metal of specific melting point. Now as current increases and it increases beyond a certain limit, this wire will break because it will reach the melting point of the wire and the wire breaks. And once the wire breaks, your circuit breaks. And the circuit breaks means no current further flows in the circuit. So we have to choose this wire appropriately. We should not choose a wire of very high melting point. In that case, it will allow very high amount of current to flow through it, because it will not melt easily. So we need to choose an appropriate melting point, so that as soon as the current increases beyond a certain limit, the wire melts and the circuit becomes an open circuit, or the circuit breaks and current cannot further flow through the circuit. Now we will introduce another important, let us now define another quantity associated with it, that is electric power. So just now we saw that the source energy got dissipated as heat across the resistor in the electric circuit. Now the rate at which this energy gets dissipated in the circuit is known as electric power. Normally we have talked about power in one of our previous lessons, where we say that the rate of doing work is defined as power. So in this case also, since we are talking about electric circuits here, so here the rate at which the electric energy is dissipated, that means the rate at which work is done in bringing the charged particle from one point to another, that is defined as electric power. So it is denoted by a capital P. The SI unit is similar to power, that is watt. So how do I define 1 watt? It is defined as the power consumed by a device carrying 1 ampere of current when operated at a potential difference of 1 volts. Because power is equal to VI. That is what we derived in the last slide, right? So if I want to define 1 watt, it has to be 1 volt multiplied by 1 ampere of current. So the power consumed when 1 ampere of current is operated, when 1 ampere of current passes through the device when operated at a potential difference of 1 volts. Now applying Ohm's law, we can also write that power is equal to V square by R, or power is equal to I square by R. Let us now try to solve few problems based on whatever we studied so far. So here comes problem 1. It says, several electric bulbs designed to be used on a 220 volts electric supply line are rated as 10 watts. How many lamps can be connected in parallel with each other across the two wires of 220 volts if the maximum allowable current is 5 amperes? So in this case, the bulb is rated as 10 watts. That means the power is 10 watts. And what is the supply line? That means what is the potential difference from the source? That is 220 volts. Right? So using this value of power and potential difference, we can calculate the value of resistance. We know that P is equal to V square by R. So using this we can say P1 is equal to V1 square by R1. So from this we can calculate R1 as V1 square by P1, that is equal to 220 into 220 divided by 10. So this comes out to be 4840 ohms. Now it says that there are several electric bulbs which are connected in parallel so that the maximum allowable current is 5 amperes. So now we are able to calculate the value of each resistance, but we don't know how many such resistances are connected. So let us suppose that the number of bulbs is N. So we assume that the number of bulb is N and the resistance of each such bulb is 4840 ohms, right? So what would be, and all these bulbs are connected in parallel, that is also mentioned in the problem. So what would be the equivalent resistance of that combination? 1 by Rp, if Rp is the equivalent resistance, will be equal to 1 by R1 plus 1 by R2 plus 1 by R3. This will be added for N times because I have assumed that the total number of bulbs is N. So now we can say that 1 by Rp will be equal to 1 by, now the values of R1, R2, R3, all these values are same, they all are 4840. So we can replace them by R. So we can say this is equal to N by R. So from this we can say that Rp is equal to R by N ohms. right? R or R1, whatever you want, you can replace it with any of these. So now we know the value of R1. Now for the entire circuit as a whole, if you look at the circuit as a whole, how much current is allowed to be flown in the circuit? The maximum allowable current is 5 amperes. And what is the potential difference across the circuit? That is 220 volts. So using this data from Ohm's law, we can calculate the value of equivalent resistance of the circuit. So if the equivalent resistance of the circuit is Rp, we can say V is equal to I into Rp, right? So from this we can calculate Rp as V by I, that is equal to 220 divided by 5, which comes out to be 44 ohms. So now we make use of this equation and we say that N is equal to R1 by Rp. So R1 was 4840 ohms. So put it as 4840 divided by 44. So this comes out to be 110. So that means in order that a current of 5 amperes flows through this circuit, we will have to connect 110 electric bulbs in parallel with each other. Let us look at the next problem. It says, compare the power used in the 2 ohm resistor in each of the following circuits. The first circuit is a 6 volt battery in series with 1 ohm and 2 ohm resistors. So how will the circuit look like? So let us look at the first part first. So you have 2 resistors, 1 ohm and 2 ohms, and they are connected with a battery of 6 volts. So this is a battery of 6 volts. So we have to compare the power used in the 2 ohm resistor. So we have to calculate the power across this resistor. Now let us first look at, how will the current flow in this circuit? Let us suppose some current I flows through the circuit. The same amount, since these 2 resistors are in series, so the same amount of current will flow through each of these resistors. So let us try to calculate the current flowing through this circuit. What would be the equivalent resistance of the circuit? 1 ohm plus 2 ohms, which is equal to 3 ohms. Now the current through the circuit will be equal to V divided by R equivalent from Ohm's law. V is 6 ohms, R equivalent is 3 ohms. So this gives 2 amperes. So that means 2 amperes of current will flow through this circuit. So now concentrate on the 2 ohms resistor, because we have to calculate the power used in this 2 ohm resistors. Now what is the current flowing through the 2 ohm resistors? 2 amperes. So current through 2 ohm resistor is equal to 2 amperes. Therefore power across the 2 ohms resistor will be equal to I square R. What is I? I is 2 ampere into R. R is again 2 ohms. So this is equal to 8 watts. So that means 8 watts of power is used in the 2 ohm resistor. Let us look at the second part of the problem. It says there is a 4 volt battery in parallel with a 12 volt and 12 ohms and 2 ohm resistors. This means here you have 2 resistors which are connected in parallel with a battery of 4 volts. So this is a 4 volt battery, this is 2 ohms and this is 12 ohms. So in this case, first of all, in this case also we have to calculate the power used in this 2 ohm resistor. So for this we will have to calculate the current through this resistor. Now what is the potential difference across these resistors? The potential difference across these 2 points is 4 volts. Potential difference across these 2 points is also 4 volts. Therefore, let us first calculate the current through 2 ohm resistor. That will be equal to V by R as per Ohm's law. So V is equal to 4 volts divided by R is 2 ohms, which is equal to 2 amperes. So here also 2 amperes of current flows through this 2 ohm resistor. Therefore, the power through 2 ohm resistor will be equal to I square into R. which is equal to 2 square into 2, that is equal to 8 watts. So in this case also, the amount of power that is used in the 2 ohms resistor is 8 watts. Here comes problem 3, which says 2 lamps, one rated 100 watts at 220 volts and the other 60 watts at 220 volts are connected in parallel to electric mains supply. Okay, so P1 for the first lamp, power is 100 watts. For the second lamp, power is 60 watts. The potential difference for the first one is 220 volts and the potential difference for the second one is also 220 volts. Now it says that they both are connected in parallel to electric mains supply. So what current is drawn from the line if the supply voltage is 220 volts? So let us see how much current will flow through this first bulb. So the current through this will be equal to P1 divided by V1. That's because we know that power is given as the product of potential difference and current. So this will be equal to 100 divided by 220 amperes. Similarly, current drawn by the second lamp will be equal to P2 by V2, that is equal to 60 divided by 220 amperes. Therefore, total current drawn by these two bulbs will be equal to I1 plus I2. So total current drawn will be I1 plus I2, that is equal to 100 by 220 plus 60 by 220, that is equal to 160 by 220 amperes. This comes out to be 0.727 amperes. So this much amount of current will be drawn from the line. Let's look at the next problem. It says, which uses more energy, a 250 watt television set in 1 hour or a 120 watt toaster in 10 minutes? So let us try to calculate the energy for the first one. For the television set, power is given as 250 watts and time is given as 1 hour. So 1 hour would mean 60 into 60 seconds. Now for the toaster, power is given as 1200 watts and time is given as 10 minutes. So 10 minutes would mean 10 into 60 seconds. Now we all know that power is nothing but work done per unit time. That means energy per unit time. Therefore, we can say that energy is equal to power into time taken. So power is 250 into 60 into 60. So this comes out to be 9 into 10 to the power 5 joules. Again, in this, energy will be equal to power into time taken, that is equal to 1200 into 10 into 60. So this comes out to be 7.2 into 10 to the power 5 joules. So if you compare the value of E1 with E2, we see that E1 is greater than E2. That means the television set uses more energy than the toaster. Let us look at problem 5. It says an electric heater of resistance 8 ohms. So the resistance is given as 8 ohms, draws 15 amperes from the service mains in 2 hours. So the resistance of the heater is 8 ohms and the current it draws is 15 amperes in how much time? In 2 hours. So we have to calculate the rate at which the heat is developed in the heater. So in a way, we have to calculate the rate at which the energy is consumed by the heater. And what is rate at which energy is consumed? That is nothing but power. So that means we have to calculate power. Right? Now convert this time into seconds. It will be 2 into 60 into 60 seconds. Now, how do we calculate power? We know that power is given by I square into R. So we really don't need this amount of time for which it takes this much of energy. So power is I square R. So I square is given as 15 square into R is 8 ohms. So this comes out to be 1800 joules per second. So this is the rate at which heat is developed in the heater. Two conducting wires of the same material and of equal lengths and equal diameters are first connected in series and then in parallel in a circuit across the same potential difference. The ratio of heat produced in series and parallel combinations would be which of these options? Now we know that heat produced is given by V square by R into T. Because we know that as per Joule's law of heating, heat produced is nothing but V into I into T. So applying Ohm's law, we can write it as V square by R into T. Now let us first look at the series combination. What would happen in series combination? Heat produced is denoted by Hs. This will become V square divided by Rs into T. What happens in parallel combination? In the parallel combination, Hp will be equal to V square divided by Rp into T. Now let us try to calculate the value of Rs, that is the equivalent resistance in series combination. This will be equal to R plus R because resistance of both the wires will be same. Because they are made up of same material, they have equal lengths and they have equal diameters. Because resistance is given by rho L by A. So if they are made of same material, that means rho will be same. They are of equal lengths, so L will be same. They are of equal diameters, therefore area will also be the same. Therefore the resistance of both the wires will be same. So let us assume that the resistance of each wire is R. So equivalent resistance in series combination will be equal to 2R. Equivalent resistance in parallel combination will become 1 by R plus 1 by R. This implies Rp will become R by 2. Therefore, the ratio of the heat produced in series combination to the parallel combination will be equal to V square by Rs into T divided by V square by Rp into T. So this V square and T will get cancelled. So we get Rp divided by Rs. Now Rp is R by 2 divided by 2R. So R will get cancelled and we get 1 by 4. So Hs by Hp will be equal to 1:4. So if you look at it, option C would be the correct option. So with this we will conclude this lesson on electricity. So what all did we study in this lesson? We talked about what is electric current, what causes electric current to flow in a circuit, how do we draw circuit diagrams to represent electric circuits, what are resistors, how do we combine resistors in different types of combinations to get a desired value of resistance to complete a circuit. So these were some of the things which we discussed here, and we also talked about the heating effects of electric current.
I hope this video on electricity was useful. If you have a feedback to share, do let me know in the comment section. I would be very happy to hear from you. If you liked the video, do not forget to share with your friends so that they can also learn from this video. I will see you all very soon with a new video, with a new topic. Till then, stay home, stay safe, take care. Bye-bye.